Hello to all of you. I am very happy to welcome you here during this virtual session of the SSCI 2020, during the Symposium on Computational Intelligence in Vehicles and Transportation Systems. My name is Florian Wirtmüller, and today I will talk about our article entitled A Fleet Learning Architecture for Enhanced Behavior Predictions During Challenging External Conditions. The article is a joint work with my co-authors Marvin Klimke, Julian Schlechtriemen, Jochen Hipp and Manfred Reichert. So let's take a look at today's agenda. First of all, I will give you a short motivation for constructing our fleet learning based architecture. Afterwards, we will take a look at the developed architecture whose essential blocks were finally applied to a testing vehicle. At the end, I will summarize the work and give an outlook on future research. As this slide shows, conventional and widely used motion prediction approaches are constructed the way the upper part of the image shows. First of all, a single data collection campaign is performed to generate a driving behavior database. The collected data are then used to train a motion prediction approach. This can be carried out in many different ways. On the slide, this is simply indicated by a neural net. This model is finally implemented on vehicle ECUs, where it is used to predict the movements of surrounding vehicles. In the case that an unknown situation that hasn't been seen during data collection arises, the system's output becomes undefined. The system may work properly or not. It is not trivial to know about that. Such unknown situations can, for example, occur if special traffic situations occur during challenging external conditions, such as rain or during the night. Mostly, these situations cannot be covered during a single data collection campaign with the same data density as frequent conditions. To overcome this, we propose in our article a continuous data collection. Therefore, all vehicles of a fleet are used to detect unknown and challenging situations. The latter can be added to the situation database, where they are used to retrain and redeploy improved models. Therefore, all vehicles of a fleet are enabled to perform valid predictions, also in challenging situations, just after one or very few vehicles have been faced with problems during that specific situation. So let's now take a closer look on our developed architecture concept. In general, the architecture consists of an in-vehicle and a backend component. The latter is only necessary once, whereas the in-vehicle component is deployed on all N vehicles of a fleet. The in-vehicle component consists of an AD stack, which itself consists of modules for sensor fusion, situation prediction, trajectory planning, and actuators. Besides, all vehicles have a communication module and a prediction watchdog. The decision of the trajectory planning module are thereby influenced by the sensor information from the sensor fusion module and the predicted environment. The output of the situation prediction module is buffered up to the prediction horizon. In that moment, the buffered prediction can simply be compared to the current sensor information. Therefore, erroneous predictions can be detected. As the prediction buffer stores the used prediction parameters as well as the sensor information additionally to the prediction output, this information can be packed and sent over the communication channel to the backend. In the backend, the package is received, added to the situation database, and used to retrain prediction models. As the sensor information can also contain knowledge about external conditions, It is also possible to train several expert models, which can be applied in special situations, such as during rain. During operation, vehicles in the field can then ask the backend for a set of prediction parameters that is beneficial during the current conditions. To show the fundamental feasibility of the system, we decided to apply the most important components of the system to a testing vehicle. To do so, we used a series-like sensor setup. In addition, we fell back to a situation prediction approach we proposed in previous work. Simply put, the approach consists of a maneuver classifier and 3 position prediction experts. The maneuver classifier indicates how likely the 3 maneuvers lane change to the left, lane following, and lane change to the right are. This knowledge is used to add up the probabilistic position estimates of the 3 expert modules weighted by the maneuver probabilities. The maneuver classifier is thereby carried out as multilayer perceptron and the 3 experts as Gaussian mixture regressors. For the sake of simplicity, we decided only to predict the future positions of the ego vehicle for this first experiment. For surrounding vehicles, the mechanism would be equivalent, but would require greater implementation efforts. The prediction buffer fixes the predicted positions, in that case the ones of the ego vehicle itself, and holds them till the prediction horizon arises. As this happens, the comparison module compares the actual and the predicted positions. If the two values should exceed a given threshold, a package would be sent to the backend in the actual application. By contrast, we decided to simply log the data locally for this experiment. Besides, we solely evaluated lateral prediction errors with a threshold value of 0.2 meters. In addition to the abstract view I presented on the preceding slides, we wanted the chance to get a feeling of our system's performance. Therefore, we used an augmented reality display that is connected to the underlying robotic operating system, better known as ROS, to visualize the prediction outputs in real time. The figure here shows how the display is integrated and displays our predictions. Besides, we prepared a short video sequence showcasing a typical situation. In the video, you can see the maneuver probabilities of the ego vehicle for the 2 maneuvers lane change to the left and lane change to the right at the bottom. The maneuver probability for lane following, which is not presented here, complements these two to a sum of 1. In addition, the most likely trajectories estimated by 3 expert models are shown from a top view perspective on the right-hand side. Besides, the full spatial probability distribution, which is the actual output of the prediction module, is shown for a prediction horizon of 3 seconds. Additionally, the memorized position estimates are shown as yellow tennis balls on the top view and in the augmented reality view. The little number over the tennis balls hereby denotes the time up to the prediction horizon is reached. This means that our ego vehicle's center of gravity, which is a little bit behind the camera, should exactly be at the tennis ball's position if the counter reaches 0. In that case, the prediction would be perfect. As our predictions are probabilistic, this can in fact not always be the case, as our actual system output is the spatial probability distribution. If we now encounter a lane change, the probability distribution becomes wide and distributed over the old and the new lane change as the position uncertainty is large. Therefore, the tennis ball, which is always positioned at the center of gravity of the distribution, is very close to the dashed lane marking. This shows that it's actually problematic to use single-shot predictions for evaluation purposes. But evaluating the distributions is in fact not possible. At this point, I would like to add that it is exactly the intended system behavior to output a distribution with a high uncertainty during a lane change, as the actual position depends on many impacts and is therefore highly probabilistic. Therefore, a good position estimate would be hard to produce also for a human driver. Let's take a look at the video a second time. As you can see here, now the vehicle changes the lane, and the point you can see here in the future is exactly over the lane marking. And now the vehicle changes the lane, and also the distribution shown here is very wide and has a large variety. And for the next lane change, we have the same behavior. Here a large variety, and now the vehicle is back, and the variety in lateral direction is very small again. After that short excursion, I would now like to come back to the samples we collected with our threshold strategy. As you remember, we logged all samples where the lateral prediction error at a prediction horizon of 3 seconds exceeded a value of 0.2 meters. With this setting, we collected data in several test drives on German highways with an overall measuring period of more than 1 hour. Now we want to take a look at the data collected that way. The shown image depicts a histogram of the collected samples' lateral and longitudinal accelerations. According to the visualization, the employed position prediction approach seems to produce more faulty predictions when negative longitudinal or positive lateral accelerations occur. This could now be a first hint that the dataset which was used to train the motion prediction models is not well distributed with respect to these two physical quantities. Our expectation is that our system will be helpful to detect similar effects if special external conditions occur. To investigate such effects more into depth, a larger database is needed. But in our opinion, these investigations demonstrate our system's fundamental ability to reveal the weaknesses of the datasets used for motion prediction. In addition, the overall system will be able to bridge the gaps in the dataset. Let's now come to the summary of our article. In summary, we presented a new fleet learning-based data collection architecture that ensures continuous improvements of motion predictions of surrounding traffic participants. This is especially beneficial during challenging external conditions. We applied the relevant elements of the pipeline to testing vehicle and showed fundamental feasibility of the whole system. As an outlook, we would like to expand the memory component and conduct investigations based on vehicles other than the ego vehicle. In addition, we would like to roll out the data collection architecture on a larger fleet of testing vehicles. As soon as a larger database becomes available, we would like to study the actual improvements of the motion prediction modules being enabled by the collected data with respect to external conditions.